Hi, I'm Richard Delaney from RopeLab in Australia. I want to make a video about carabiners and some of the different things we look at with carabiners. One of the most important ones is I'd really only recommend buying carabiners from the common brand names that you recognise and trust. And when you buy those, buy them from a reputable supplier where they can trace the supply chain from what's on the shelf and going in your hand right back through the manufacturing process. There are many common brands that you'll all be familiar with, just stick to those. With those brands, depending on their intended use, there could be a couple of different standards that they're certified to. It might be one of the American ANSI Z359 standards, for example, or the NFP 1983 standards. If you're in Europe, it'll be EN 362 or EN 12275. And just be aware when you see that number EN 362, there should be another number after that. It's required as part of the European standard. So if it says EN 362, it will say something like that CE symbol followed by a 4-digit number like 1016. That number corresponds to the certifying or the test laboratory that confirms that that particular carabiner does meet the requirements of that EN standard. So what strength are we looking at and how's that determined? Well, generally, all the standards, they're slightly different, but it's going to be something like get a pair of 12mm pins and pull them apart at a controlled rate and see where that carabiner fails. And then after they do a batch of those, they'll apply a statistical treatment to that to forecast what the minimum strength that that carabiner should break at. It's not possible to guarantee that that's the minimum, but each of them, the different standards will have different ways of saying that's the minimum breaking strength or the MBS for that carabiner. So there'll be a couple of different requirements. There's the long axis or parallel to that spine, MBS. There'll be across the carabiner this way. The new requirements, you'll see a lot of these carabiners with these larger gates. Some people call them ANSI gates, but it's the gates that are required under the ANSI standard to withstand a 16 kilonewton force in that direction. And there's also a long axis gate open strength, so that direction when the gate's open. I'll come back to strengths and when I talk about shapes a little bit more later. The other topic which is often hotly contested is the material that these carabiners are made out of. So I've got two carabiners here. One is steel and one is aluminium. Which one is stronger than the other? Well, you can't determine that solely based on the material because it depends on the shape and the configuration and the way the test is conducted. But the bottom line is, with these carabiners, if you read on the spine of this steel carabiner, it says that the MBS, the minimum breaking strength of that is 30 kilonewtons, then that is the strength that we need to know when tested in accordance with that standard. This aluminium one, is 25 kilonewtons. So according to that standard and the way it's tested, that one is 5 kilonewtons weaker than that one. My issue with those strengths is that assumes that we're putting two 12mm pins in here and pulling them apart. We don't often use these to connect 12mm pins together. It's more likely to be things like 10mm ropes or maybe even really narrow dynamer slings or through bolts on structures, all these sorts of things. So the in-use strength will be quite different. A 25mm wide piece of tube tape or sling will give a different strength, as will the three-way load that people often talk about when we're looking at these. That's materials. I'm going to come back to those loading scenarios and how they might derate or weaken the carabiner in use in a minute. But another thing on material, aluminium versus steel, I think it was part of an advertising campaign when aluminium was becoming more prominent with the construction of engine blocks, and I certainly remember it for bicycles. And lines like steel is real, and aluminium like this it can be good 1 minute and suddenly explode the next, whereas steel will bend before it breaks. Look, forget all of that stuff. This is not 100% pure aluminium. And this is not 100% pure Fe or iron or steel. These are both alloys of different materials. So this might have some magnesium in it. This has different levels of carbon. There's a whole bunch of reasons that will make these different types of materials. Is it a stainless steel carabiner, which might be more brittle? Is it a 316 series stainless or a 304 series stainless, for example? This carabiner here is at a 7075, 7000 series aluminium with a T6 heat treatment, or is it a 6000 series aluminium alloy that's manufactured from? So it's not as simple as saying steel versus aluminium and one is better. People talk about the susceptibility of aluminium carabiners to withstanding impacts if we drop them on hard surfaces. Look, that can't be ruled out. But based on a bunch of tests that I've done and other people have done, I'm not satisfied that those impacts, if the carabiner is not physically obviously damaged, I'm not convinced that it's necessarily weaker just because we dropped it. Having said that, if I was to drop that 50 meters off the side of a building and it landed on a concrete footpath, then I certainly would remove that from service. If I was to drop it from here onto the floor in front of me, I'd go through the usual thorough visual and functional inspection by a competent person and probably deem that that's appropriate to put back into service. Does the steel withstand that any better than the aluminium? I can't say that it does. Another key difference between these two materials is their potential to fatigue. It's something I wish I knew a little bit more about, but one thing that from what I understand is if I cyclically load this over and over again with a 1 kilonewton load, it should have theoretically an infinite life. It's not going to degrade suddenly with that fatigue, whereas the aluminium is more susceptible and will reach that fatigue limit and that cumulative fatigue limit at some point. Interestingly, this is a DMM carabiner, and I asked Fred Hall at DMM, you know, what is that designed for? How many cycles to be loaded to, say, 1 kilonewton or a one-person body weight? And he said, you know, it's too hard to determine that because it's more than 100,000. And if you think about load that up, reach that load at a controlled pull rate, and then relax, let the thing relax, and then do it again, how much time that would occupy a test bed for, and how many carabiners you'd have to do that to, and every single shape and every subtlety in manufacturing difference before you could come up with a reasonable number. But what he did say to me is, I can guarantee that that mechanism there will wear out long before you reach the fatigue limit of that 7075 T6 aluminium carabiner. I thought that was a pretty neat answer from Fred. So that's probably enough on the materials. Bear in mind, just while we're on the steel carabiners, of course, there are many older ones like these Stubai. Some of you will recognise these. Locking screw gate carabiners, HB ones. This one's just a plain, no, it's a triple action gate with a captive bar underneath it there. This Kong one, Austria-Alpin and DMM. Oh, sorry, that DMM one's not steel. This one here is. And then this Petzl Oxan as well. So there's a whole bunch of steel carabiners. Oh, there's another Kong one that a lot of people will be familiar with. It's very common on industrial rope access sites. That plain Jane, bread and butter, steel screw gate carabiner that Kong have made forever. That steel Petzl Oxan meets all of those standards we were discussing before. That gate's a little bit more beefy because it's now this 16 kilonewton externally applied force concern. Let's talk a little bit about the shape, and I'm just going to flip over to the other camera here because I've got a whole bunch of carabiners in front of me, and I think, in fact, if I just go to a true oval shape like this one here and then compare that with this really aggressive D shape, just think about a couple of things for a minute. I think we've been a little bit dudded, or in fact I might even go to these two here. This is a slightly offset Chenard oval carabiner. This is a Metolius offset D carabiner. Think about what happens when I load that up between the two 12mm pins. They'll be positioned approximately here and here. And as I load that up, we're going to see some loading of the gate and some loading of the spine. If it was a true oval like this shape, those loading points are going to sit midway between the spine and the gate. So as I increase that load, we should see 50% shared strength between those two elements. Whereas this aggressive offset D, it's going to shift it all across to the spine and be really parallel to the spine. So maybe you can see straight away, if I compare these two carabiners, it might even be more fair if I compare these two. This is a 24 kilonewton carabiner. This one here is 25 kilonewtons. There is more material in that one. Maybe if we look at these two, approximately the same amount of material, 25 kilonewtons, and this one is 30 kilonewtons along the long axis. Why is that? When I load up those two 12mm pins, it's pulling the spine in tension. So that is a stronger shape than this shape here, which will keep the pins and put some of, like half the force approximately on the gate and half on the spine. So that looks stronger and sounds better. However, when it comes to actual use, if I want to think about putting a couple of ropes in this carabiner, so I put 2 ropes in here and my descender or some anchor in here, I am going to have this loading scenario which is not right where the 12mm pin would sit. In this carabiner here, if I put 1 rope here and 1 rope here, one's going to sit here. We can see now we've inadvertently shifted some of the load away from the spine, and we're going to be putting an opening force on the nose. So that will result in a lowering of the strength in actual use from 30 maybe down to the 25. This one here, even if I put 2 ropes there, it still centers the load. So if that's 25 in the tests with the 12mm pins, it's still going to be 25. So I think that's a better shape. Then if I add the complexity of putting pulleys, and particularly fixed side plate pulleys, you'll see that the pulley is going to sit centrally in there, something like a microtraction, whereas here it's going to sit at an angle. It's not going to sit really nicely. So there's a couple of subtleties in the shape there, which are quite different. I'll just go back to the climbing sort of style carabiners, the non-locking carabiners. That one's slightly locking. And look at some of the differences in there. Bent gates versus straight gates. The bent gate was simply to make it easier for climbers to clip that rope in when they're reaching up to grab it. However, that should not be used to clip to another piece of hardware because of the potential for that to load up and roll out. It's much more enhanced with a bent gate carabiner over a straight one. Wire gate carabiners, it took us a long time to, I remember in the 90s when these black diamond hot wires came out, to accept that shape as being appropriate. Like, how can it be as good as that? But in fact, it's easier to manufacture, it's just as strong, and one of the most important things is it's not subject to that potential you can imagine as a climber. If you fall, and at that moment where the rope comes under tension, that carabiner is going to hit the rock face. There's almost no mass in this gate, so it stays closed. Whereas if we've got our rope clipped into this carabiner, because there's so much more mass there, you can't see it on the camera, but you can hear it. That's the sound of this gate opening ever so slightly as it hits the rock, which is also the point where the rope puts the most tension on the carabiner. So it's the most critical time, and now we're looking at the gate open strength of that carabiner rather than the gate closed. So 24 kilonewtons gate closed, only 9 kilonewtons gate open. I think it's possible, it's unlikely, but possible to put 10 kilonewtons on a carabiner during a bad fall. Whereas this one here, I can't get that wire gate to open with that same impact. So different mechanism there. Let's have a look. That's the more modern of that one, the new black diamond one. This is an Edelrid slider, which just has a really subtle locking mechanism on the gate here. Which just for those key moments where you really want to be sure your rope doesn't roll out or your gate doesn't open, I think that's not a bad compromise in terms of weight. I will show this one other variation on the wire gate carabiner here. Unfortunately, Rock Exotica doesn't make this one anymore because people didn't quite get it. Is it a double action carabiner? Well, you do have to move 2 components to get the rope in there, whereas this is just a single action carabiner. And people were mucking around with these readies going, oh, it's really awkward because I've got to hold both open to get something to clip in. But with a bit of practice, you'd work out to get something out, I just need to open one of the wires, and to get something in, I just need to open the outside wire and I can clip it in. So I think that's a really interesting mechanism. I would call that a locking carabiner. And having done a little bit of stuff in cold environments where carabiner mechanisms can freeze, whether it's a screw gate carabiner or a triple action auto locking carabiner, or where's that other, this guy here, the old black diamond super locker, triple action Rubik's Cube sort of style. You get water in those and they freeze, and you've almost got to get that unfrozen to get it unlocked. This one will not freeze. Similarly, in canyon environments, if I'm using screw gate carabiners, Blue Mountain sandstone gets in here and wears those out really quickly, and soon they just become sliding sleeves, whereas this doesn't wear out. So for canyon guiding, which I used to do a lot of, and working in cold environments, these are lightweight and not prone to those aggressive, abrasive or freezing events that can prevent you from opening them. While we're on different mechanisms, let's have a look at a few more. So the screw gates, we've mentioned, people are pretty familiar with those. By the way, it doesn't matter on the age of these, even this old Stu-by one here, nowhere, anywhere in any of these manuals have I seen an instruction that says tighten this up as far as you can and then back it off 1/4 of a turn. It does not say that anywhere. Most of the manuals, they'll say ensure that it is locked and secure. To me, that means do it up tight. If I can't get it undone because it's been loaded up and someone's tightened it up a bit more, then all I need to do is put a bit of tension on that, and then I should be able to unlock that. This older mechanism, this clog one here, when I lock that sleeve, it does actually bind on the nose. Whereas more modern locking carabiners, you'll see if I screw that gate all the way up, there's still a bit of movement in the gate there. It hasn't actually locked on the nose. So there's nothing wrong with doing that up tight. If you stretch it, you can't do it up any tighter because it's bound on a mechanism within the gate, and then I can open it up again. So this whole thing about do it up and then back it off 1/4 of a turn, just forget you ever heard that if you have. Let's have a look at these two. So this clog, I mean this HMS shape was, HMS actually stands for the carabiner, which is designed to have a Munterhitch put on there. I won't make a fool of myself and try and mispronounce the Mastversicherung, I think it is, the carabiner, the Munterhitch. But that's why that shape is called an HMS carabiner. It is the carabiner designed for a Munterhitch. Clog also brought out this twist. It's just a twist to open, so that's double action. You can see there, you have to look at the pin, and you can see there's no requirement to lift it up. It's just twist, and then it opens. Slightly more secure than the non-locking, and not prone to vibration like the screw gate can be, which, out of interest, doesn't matter. Gravity with the wrong mode of vibration, whether the carabiner is orientated up or down, that vibration can still cause that gate to open. Some other mechanisms that I've got here, this, and again I often cheat just by looking at the pin, and I can see to open that, I need to turn it slightly, pull it up, and then open it to get that gate open. That is a triple action auto locking carabiner. This one is also this Petzl one that you'll probably recognize, the old AMD triple action auto locking, the newer shape Petzl AMD triple action auto locking. Now, I should point out with all of these triple action auto locking carabiners, if I hit those the wrong way, like that is locked. You can see it's locked there, and I'm opening it just by hitting it on something. So those mechanisms can be defeated, whether they're the doubles or the triples, and it doesn't matter whether it's the DMM ones or the Rock Exotica ones or the Petzl ones. We can defeat those mechanisms. So none of them are super secure. The one that I have found that I can't defeat, and a lot of people don't get this one, but there are times when I have, if I want to be absolutely sure I've got a single carabiner in the system which is prone to interference with performer clothing or other things, I want to be sure that there's no way that can come undone, and I can't defeat that mechanism. I'm sure if I came up with something really contrived I might be able to, but this is a 4-action carabiner. I have to first turn the purple sleeve, I have to lift it up, and then I have to turn the purple and green sleeve back, and then I can get the carabiner open. So it seems like a lot of overkill there, but I can see times where I want that extra security if I've got everything completely dependent on a single connector that I don't want to be able to come undone. This one here, that might pass that, but they don't make that anymore. I think this is the first one that Black Diamond made, and you can see the sort of the Rubik's Cube mechanism here. I've got to hold that half up to twist it, and then I can get the gate open. It's got a twist lock ready to go position, as well as then the super locked position that you've got to hold your tongue in the right place to get that one open. What other mechanisms? Oh, this is one of the original ball lock ones, the plastic mechanism that it did get a little bit problematic with age, and then they replaced that with this ball lock mechanism. You actually have to push the green ball before you can spin that to get it open. So 1, 2, 3 action auto locking carabiner. Some people love those. I've used them a couple of times, but they're not my favorite. This is a rather unique action from Austrialpen, where you can either open this end or this end. So to get something in, I need to hold it that way, and then I can open the other end, and I can't get that out, so I can open that one to put it in. Look, I've got a couple of those. I'm sure there is a really good place for those, but I haven't found it. Yet. So look, I think that's enough on materials, shapes, mechanisms. One key thing I want to talk about, I'll just move all those away while I make a bit of noise. And I've got a set of carabiners here which I take on all my workshops with me, and those who've done a workshop will recognise these, I'm sure. They're CT, Italian-made carabiners. CT is an awesome brand. You're probably not too familiar with their products, although now that they've got a few out under their own name, you will be, with things like the Sparrow and the Roland Lock. But they've actually made many carabiners for other companies, and I think, as an example, this Petzl OK carabiner, that's actually made by CT in Italy. Many companies have carabiners made by other companies. That original Petzl AMD was made by Rock Exotica in the US, as an example. So many companies have made products for each other. They all get on with each other pretty well. But look, let's have a look at these CT carabiners here. They're all the same model of carabiner. They're not all the same batch. But what I've done is I've put them on the test bed and applied a particular force to them. You might not be able to see, but I've got 18.30 engraved on the gate of that. This one doesn't have anything engraved on the gate. So I didn't actually put that one on the test bed. Those two, functional and visual inspection, look the same. And I should be pretty happy with that. What I don't know from that inspection is that one's been loaded to 18 kilonewtons. I only know because it's written on the gate. If I did get a micrometer and measure that, I would find this distance here and this distance here are slightly different on that carabiner. Let's move on to this one here, and it starts to become a little bit more obvious now. This one's been loaded to 20.19 kilonewtons, and hopefully you can all see it plain as day. This one here is loaded to 23.32 kilonewtons. The 3 sigma MBS for this is 22 kilonewtons, so that one I pulled that one harder than what it's rated to break, and I would expect that for any carabiner. It should withstand more than the rated strength that's marked on the gate. Once. It might not last a second time, but it should last at least once. But the key thing here, remember that statement I said before about people find that aluminium, it might just explode, or that was the myth, they don't stretch. I mean, that is an example of a stretched carabiner. If you've ever had the chance to watch one of these things being put on a test bed and broken, you'll be amazed how much they stretch visually and deform before they break. My concern is if we have people doing their own and insist on doing their own equipment inspections, and there's many companies now running awesome PPE inspection courses, what level of detail, how much attention are you paying to the inspections that you're putting in these carabiners? Are you comparing them to the original shape? Hopefully people would notice that one, but I wouldn't be surprised if they didn't. But I suspect if I gave people this carabiner and asked them to do a thorough functional and visual inspection on it, apart from the fact that it's been engraved on the gate there, they'd say, yep, that one passes. It's not until I hold that next to the original that I can see that it's slightly out of shape. So you should always be comparing a carabiner with a good one as an example. And that's been well overloaded. It still hasn't exceeded the MBS. that's only 20.19 and it shouldn't break until 22. But the key thing I want to say here is that they will start deforming, and we call that plastic deformation. Elastic deformation is I can stretch that carabiner. We all know we can see movement in carabiners just by stretching them between our hands. That's elastic deformation, and it returns to its original shape when I relax. This plastic deformation, it hasn't returned to its original shape. And that has certainly significantly fatigued that component. 18.3 kilonewtons, 22, it's still like 4 kilonewtons under, and it has undergone some plastic deformation. So the key question is, how far can we load these things? What is the design factor that we should expect out of carabiners when we're using them in normal use? So this 22 kilonewton carabiner, or let's go more conveniently to the work environment, and I'll choose a typical carabiner that I might use at work, like this Rock Exotica triple action auto locking offset D-shaped carabiner that's rated to 29 kilonewtons. How much should I reasonably be able to expect to put on that at work in normal use? It used to really frustrate me, the answer that manufacturers would say, what do you mean? It's PPE, it's designed for one person or maybe two people in the case of a rescue. And that's all I need to say, because it is PPE under all of those standards that we mentioned before. We don't need a number on that, like can I lift 500 kilograms or 1,000 pounds or whatever it is with that carabiner. It's just like, I don't even understand why you're asking that question, because this is for people. It's not for equipment and goods. It's not for materials handling. But if you really push on it, like what is that number? I could say, how far can I expect to load that and get that 100,000 or million cycles out of it before it actually fails at that low value? There's one manufacturer that makes a statement along those lines in their instructions, and it's Kong. And Kong says in their instructions, so when that Kong piece of hardware there, for example, the frog connector that they've got, or the other Kong carabiners I've got on the table here, Kong actually say for any of our hardware, do not exceed 25% of the MBS. So they're saying it's got a design factor of 4. If that was a 30 kilonewton carabiner, then what they're saying in normal use would be divide that by 2 is 15, divide that by 2 again, never exceed 7.5 kilonewtons on that carabiner in normal use. So a quarter of the MBS we should never exceed. If we stay under that 1/4, then we won't get those massive deformations, those massive changes in shape. And again, holding those two up, you can see how much that carabiner has been elongated by overloading it. So look, there's must be close to half an hour conversation just talking about carabiners and many of the things that I hear and see, and not many people seem to understand them well. I hope you found that useful. I'll try and do a few more in these series. I might talk about ropes next, and slings and harnesses, helmets, and try and go through most of the equipment that we use in the different environments we use it. Thanks very much.